Hello and welcome to lecture 5 for the introduction topic. In last lecture, we were discussing about the correlation of our diffusing passage with the compressor blade, and we have realized this compressor blade is basically making a passage that's what is of diffuser size and diffuser shape. Then we were discussing about the construction of axial flow compressor, and we realized this construction of axial flow compressor we are having say combination of passage, say my blade passage it is comprising of diffusing shape, and my flow passage or flow track we say because our axial flow compressor it is comprising of number of stages. Okay, so at the exit we will be having our area to be lower compared to my entry area to the compressor stage. Then we were discussing about the concept of aerofoil, and that's what is applicable to our axial flow compressor. Many times people used to say what is the use of aerofoil, and now you must realize like the lift force that's what is happening because of the streamlined body called aerofoil, we are getting the benefit in sense of compression. Many times people used to bend the plate, and that also they are considering as a blade. Yes, that also can be used as a blade for making of fan, but just realize one thing, what pressure rise we are expecting that's what is say large. For say curved blade, that pressure rise will not be achieved as per our expectation. Okay, then we were discussing about the Euler's equation and its application. Okay, then finally we have end up with our flow field, that's what we have discussed within our stage at particular station using our velocity triangle. Okay, and now we are aware of different velocity components. Name a few, saying like peripheral speed, that's what we are representing as say u. My absolute velocity, that's what we are representing as say c. We are representing our relative velocity as say v. Okay, we are having axial flow velocity component, we can say it's a flow component, and that's what is represented by CA. When we say we are having whirl component or tangential velocity component, that's what we are writing as a CW. And in last lecture only we were discussing about our fundamental equation for Euler's, and from that equation if you look at it says in order to increase your compression work or power input that's what is required for compression, that's what is a function of my peripheral speed and my tangential velocity component. Okay, so it says if I'm looking for increase of my work, then exit whirl component that's what we are looking to be large, and that's what we have discussed here. Say if we are looking for that kind of configuration, the change of velocity, that's what is say my relative velocity, that is what is very important. Okay, with this let's try to move ahead. Now what all we know, this is what is representing my aerodynamic configuration. Now let's try to understand this compression process using thermodynamic aspect. Okay, so here if you look at my process for compression, that's what I am representing in sense of say we are having TS diagram. Okay, so if I consider I will be having my pressure, that's what is say entry pressure P01, and my exit pressure I am writing as a P03. Okay, ideally I can assume my compression process as a isentropic process, and that's what is say my entry temperature I am writing as say T01, my exit temperature we are writing as say T03S. This is what is representing my ideal condition. So you can say this is what is the temperature at the exit of my compressor, and if I am assuming this process to be ideal process. Okay, so compression process ideally we are assuming as isentropic process in which my entropy that's what is remains constant. Now in actual condition if you look at my scenario, that will be different. Okay, let me show that process. So here if you look at, this is what is representing my actual compression process, and if you look at carefully here, this temperature T03 that's what is say higher compared to what is my exit temperature if I am considering my isentropic process. and this is what we say it is the actual temperature, that's what we are getting at the exit of my compressor. Now the question may arise, what is the reason why we are getting this much temperature rise? So this is nothing but that's what we are representing in sense of change of entropy. Now this rise of pressure, that's what is because of the losses which are incorporated with the process. So in compression process we will be having say aerodynamic losses, we will be having thermodynamic losses, and this losses in terms of thermodynamics we are talking as say irreversibility of the process, and this irreversibility, that's what we are representing as entropy term. So it says in actual process I will be having irreversibility, that's what is increasing, so my entropy, that's what is increasing. Now here if you look at, if I want to represent the work done by my compression, that's what it is written in sense of say ideal work done, that is given by say mass flow rate into delta H. Here at this point we can represent this is what is say my actual work. Now being an engineer, always we are looking for the terminology, that's what is say efficiency. We engineers are very choosy, okay, and we are always differentiating, we are looking all devices in sense of efficiency. So for compressor, people they have defined their compressor efficiency as a adiabatic efficiency. Suppose if I am considering I will be having number of stages, for that it is defined as a polytropic efficiency. So let's try to look at what is the meaning of this efficiency. Okay, so if I am representing my compression process again here, you can say this is what is my representation for say isentropic temperature rise, this is what is my actual temperature rise, or we can say this is as say my enthalpy rise. Okay, now what we know, efficiency, what we are writing as say my ideal work divided by actual work required. Do not get confused. Many times people used to say if I will be taking this as a reciprocal, then my efficiency will be coming more than 100%, and that's the reason why we are putting this. Remember one thing, this compressor device, that's nothing but it's a power consuming or work consuming device, and for that the reason why we are representing our efficiency in sense of say ideal work done divided by actual work done. This is what we can represent in sense of my enthalpy, I say H03s minus H01 divided by H03 minus H01. This is what, if I am assuming my Cp to be constant, that what we can represent in sense of my temperature ratio. Okay, this temperature ratio here, this process of compression as we have discussed, it's an isentropic process, so we can use our isentropic relation in order to calculate what will be my temperature ratio. So that's what we can correlate using my pressure ratio. So here this is what P03s by P01, this is nothing but that's what I am writing as say my pressure ratio. Okay, so this is what is say my pressure ratio. If I am putting this together, it says my adiabatic efficiency. People sometimes used to say that as a total to total efficiency for the compressor, it's a function of my pressure ratio and temperature ratio. So this is what is a correlation, that's what we are using for defining our adiabatic efficiency. Okay, so this is what is representing the adiabatic efficiency of our compressor. As we go along, this term that will be coming repeatedly, and that's the reason why we need to be fundamentally clear from the beginning. That's the reason why we are having this definition. Okay, now here what we are discussing, that's what you will say, this is what is say my pressure ratio. This pressure ratio I am talking about the overall pressure ratio. Let's try to understand what is happening when we say we are having stage. So here say this is what we have discussed. I say I am having my rotor and stator. Okay, my entry condition I say it's a station 1, exit condition from the rotor is station 2, and exit of my stator, that's what is say my station 3. If I am considering I will be having my air that will be sucked from the atmosphere, that will be having say pressure P1, it will be having my temperature say T1. Okay, now what is happening? My flow, that's what will be get sucked inside my compressor rotor specially. Okay, when it is getting inside, what will happen? It will be achieving some kind of kinetic energy. That's what I say, it's C1 square by 2Cp. So you can say this is what is a T1 plus C1 square by 2Cp. That's what is representing my total enthalpy or my total temperature. And somewhere here I am putting this pressure as a P01. Okay, so this is nothing but that's what is called total pressure. So my flow in compressor, it will be entering with total pressure P01. So as we go along, we need to remember we are more interested in total property compared to our static property. Okay, because my fluid, that's what is flowing through this machine, it's a continuous fluid. Okay, so our interest, that's what is now on say total property. So I will say my pressure at the entry of my compressor, that's what is say P01. Now what is happening? During my compression, I will be having the rise of pressure. So you can say my pressure rising from P01 to P02. Okay, so at that station I will be having my temperature say T01, or I can say my enthalpy as say H02. Okay, so this is what is representing my total enthalpy or total temperature T02. Now what is happening? Now I will be having say this process, that's what is happening in my stator. Say rotor, that's what is, we can say it is doing my compression work. There is no work that's what is being done by my stator. Okay, so we can assume the process to the stator as a adiabatic process. Okay, so we can say my T02 and T03, they both will be same. So my total enthalpy, that will remain same. But here if you look at, I will be having some losses, that's what is happening in my stator. These losses are because of frictional losses, it's because of my aerodynamic losses. Because you can understand my stator blade, it is made up of say solid body. So you can say there will be drop of pressure from P02 to P03. So this is what is representing my total pressure loss. Okay, so now you can say at the exit I will be getting my pressure as a P03. Now in line to what we have discussed, say if I'll be considering my absolute velocity, that's what is coming out from my stage, that's what I'm putting it here as a C3 square by 2Cp. Based on our fundamental, I can locate my static pressure at the exit of my stage. Okay. Similarly, if I'll be talking about say exit of my rotor, I will be having my absolute velocity, that's what is say C2 square. So I can locate my point, say my point 2. This is what is representing my pressure P2. So just understand I am having say P1, P2 and P3. So if I'll be representing this as a process, then I can say from 1 to 2 I will be having rise of pressure, that's what is my static pressure rise. Okay, and this is what is happening inside my rotor. I will be having the rise of pressure from station 2 to 3, that's what is happening in my stator. Okay, now if we are talking, as I told, we are more interested in total property. So basically if you look at carefully here, this is what is say station 01 to 03 dash, that's what is representing my isentropic process. And you can understand if I'll be joining say 01 to 03, that's what is representing my actual process. That's what is happening in my stage. Okay, so if I say here, if you look at carefully this absolute velocity component C3 square by 2Cp, or you can say C3 and C2, if you compare what is happening when it is flowing through my stator, this absolute velocity, it is going to be reduced. Okay, and that's what is representing the rise of my pressure. Now in many designs, people used to prefer this inlet absolute velocity and exit absolute velocity to be same. We will be discussing about this aspect very soon, but what they say, this is what is we are expecting our work done to convert the static pressure rise to get the density change, and that's what will be giving me my expected absolute velocity C1 and C3 to be same. Okay, now here in this case, if I say I want to define my compression work, then thermodynamically that's what is being represented in sense of rise of total temperature. So this total temperature I can write down, say delta T0. Okay, so let me put here, this is what it says my thermodynamic work. So here if you look at my thermodynamic work, that's what is represented as a m dot Cp into delta T0. Okay, now many times people they are getting confused in sense of T03 and T02, but remember what we have assumed our process, that's what is happening in my stator, that's what is a adiabatic process. Okay, and that's the reason why I am writing that as a mCp T02 minus T01. So this is what is all about, say what is happening in my single stage of axial flow compressor. Okay, now like this is what is a representation as we have discussed, that's what is talking about, say my compression process, that's what is happening in my axial flow compressor. Now this axial flow compressor, that's what is mainly been used for compressing of this gas. Okay, now when we say air we are considering as our working fluid, we can take that as a semi-perfect gas. Okay, so when I say it's a semi-perfect gas, it will be followed your Boyle's law, that means your PV, that's what is a function of my temperature, or product of pressure and volume, that's what is a function of my temperature. At the same time you will be having vanishingly small Joule-Thomson's coefficient. It says my dH by dP at constant temperature, that will be coming 0. It says my enthalpy also is a function of my temperature. Okay, but for this configuration we can say our specific heat, what we say Cp and Cv, that's what is varying with the temperature. Okay, now when we are considering our ideal condition, for that we are assuming our working fluid as a perfect gas, and when that is what is your case, you can say you will be having your Cp and Cv to be constant. We can say my enthalpy, it's a function of my temperature. Okay, so like this is what is very fundamental and that's what is required. So when I have started with the class, the time we have discussed, we are having this axial flow compressors, they are having various kind of applications. One, that's what is say for your land-based power plant. Second, that's what is for your aero application. And we have discussed some of the say industrial application where my working fluid, it is other than air, it may be gas. Okay, so we have discussed about the supercritical CO2 cycle, or we have discussed about say supercritical CO2 power plant. So you can understand under that condition you need to have your fundamental understanding of this all terminologies. Let's move. This is what we know. When we say when gases are other than say air, what we are considering, then there will be change in say your molecular weight, and that's the reason why you will be having variation in your gas constant as well as you will be having variation in your specific heat. Okay, so here if you look at, this is what is a table, that's what is representing different kinds of gases. That's what people they are using these days. So especially say these compressors, they are being used for these different kinds of gases. We will see what all are the importance. So here this is what is representing my gases, my molecular weight, gas constant, my specific heat ratio, and speed of sound. That's what we can say, it's root gamma RT. But that temperature, it is say 288 K. Now here in this case, if you compare the value of my specific heat for Freon, that's what I say, it's around 1.1, and when we are talking about the argon, that's what is having specific heat of 1.67. Same way if I am comparing my say speed of the sound, that's what I say around 138 for my Freon, and if I look at it say my hydrogen, that's what will be having my speed of sound to be very large. So like we are having the variation of this property, that's what is a drastic variation in the property. Okay, now like if I compare these two, say air as well as for Freon, and if we look at carefully my speed of the sound, that's what is almost say 3 times kind of situation. Now let me tell you what all is the use of this. People they are doing different kind of testing for different applications. Okay, now suppose say I want to test my compressor at high Mach number condition. Okay, So if I'll be using air as my working fluid, maybe I need to rotate my wheel at very high speed. Okay, and it may be having some constraints in sense of, like mechanical constraints. So in order to avoid that kind of situation, many times people, they are using say Fuel 11 as a gas for initial testing. Okay, so same kind of situation what we have observed for our wind tunnel testing, it's a kind of same. Okay, same way if you look at say people, they are using helium gas. So these days people, they are moving towards say application of your cryogenic fluids. Okay, for that application, for cooling application, you are looking for say helium gas, where you are looking for say different kind of say compressors. So helium gas compressor, that's what is very common in application. Now in order to test those kind of say helium compressors, what they are doing, they are rotating or they are using say axial flow compressor using air as a working fluid. Okay, that's what will be giving the benefit, and that will be rotating at comparatively low speed as compared to when you are rotating that wheel using your helium gas. Okay, so just understand, like based on the understanding of these properties, people, they are making their testing. So testing facility development, that is also a one kind of skill, and that's what is demand for. So in Europe and in US, if you look at many universities, they are having their own testing facility which are being sponsored by different companies. Okay, and their initial testing of their compressor or their blades, that's what is happening in their university level testing. Okay, now as I was saying, like when we are having our property to be different, under that condition we need to go with different property test. Okay, and for that you need to use your Muller diagram for different working fluids. So be careful, some assumptions what we are making that may lead to put you in trouble. Okay, so when I say design of axial flow compressor, you will say, sir, you are teaching axial flow compressor design for air. You have not discussed anything about the working fluid, but you must realize this is what is a fundamental what you need to learn, and later on you need to apply for your working fluid or your kind of working fluid what you are looking for. Okay, now say as I was discussing, this is what is representing my say your overall pressure ratio for the compressor stage. If I say my compressor, it is comprising of number of stages. If I say for say axial flow compressor, it is made up of say maybe 10 stages. Okay, so this is what is representing overall pressure rise, or you can say this is what is representing overall compression process. What we learn is, suppose say I want to do my compression from say pressure P02 to P03, I will go with number of stages. As we have discussed earlier, say my axial flow compressor, it is very sensitive device and it is having aerodynamic limitation, and that's the reason why we are going with number of stages. So that's what we are doing. Suppose if I consider I am making my compression process by using different number of stages. Let me put this process what we have learned from our TS diagram. So for my first stage, you can say this is what is representing my isentropic compression. This is what is representing my actual compression. Now this temperature, that's what is coming out from my first stage, that's what will be entering into my second stage. That's what will be going for say isentropic compression. In actual, I can say I will be having my temperature to be large. Similar to that, if I will be putting say for my third stage, I will be having this temperature rise, that's what is say T03s, and this is what is representing my T03. Okay, now remember one thing, like these compressors, they are being designed for particular efficiency, and that efficiency, that's what we are defining as a polytropic efficiency. That's what is per stage efficiency. Here this is what is representing overall efficiency. Here we are looking for say polytropic efficiency. So designers, they are preferring when they are doing their design for say LP stage or say for HP stage, they are trying to put that polytropic efficiency to be constant. okay, and that's how they are doing their compression work. So here if you look at, you can clearly compare this delta S. So here for this case I am having my delta S, that's what is coming to be large. Let me come to the point what it says. Here if you consider, say, vertical distance, if I will be putting, I will be adding together for my isentropic process, it says from my T02 to T03S, my delta T0, that's what is coming to be large. Okay. Now here for my, say, actual compression process for overall stage, if I will be considering my delta T0, that's what is coming to be lower. Okay. Now what it says, here in this case it says my elemental rise of temperature, that's what is giving me my delta T0 to be large. What is happening because of that? Suppose say I am doing my calculation for overall efficiency based on these temperatures, and if I will be measuring or will be calculating my efficiency based on these temperatures, it clearly says I will be getting my overall efficiency, okay, that's what is lower than that of my polytropic efficiency. Okay, so you can say my polytropic efficiency, that's what is coming to be large, or that's what is large efficiency, and my adiabatic efficiency, that's what is, say, lower efficiency. So you know, like when people they are bidding for supplying of their engine, or say when they are supplying their compressor, they used to define some number. Say as a customer you will be asking what is my, say, what is your compression ratio and what is your compressor efficiency. Remember one thing, what efficiency they are defining. If they are saying, say, efficiency is 90%, just realize and ask straightway which efficiency are you talking of. Is it polytropic efficiency or adiabatic efficiency? Okay, so you know, like this will give you misguiding sometimes. Okay, now let me put this in sense of, say, calculation of my polytropic efficiency. So here if you look at my efficiency, I am writing in sense of delta H0S by H0. If I am talking about, say, small elemental part, I am putting that as a dH0 by dH. We know from our fundamentals of second law of thermodynamics, we can write down T0 ds, that's what is equal to dH0 minus dP by rho. We know this is what is, say, my isentropic process. For that I am putting my ds, that's what is, say, 0. It says I am calculating my isentropic enthalpy rise, that's what is given by dP0 by rho 0. Now let me put in sense of definition of my polytropic efficiency. Here if you look at, so this is what we are writing. Okay, I am putting that as a dH0 by ds. This I am putting as a dP0 by rho. This rho I can represent in sense of P upon RT. Let me put it here. This H0 I am writing in sense of Cp T0. Okay, if I will be putting together and if I will be making my integration, it says my pressure ratio per stage or for particular elemental stage, that's what is represented in sense of my temperature ratio, and this is what is in sense of my polytropic efficiency. So my overall efficiency, that's what is a function of my, you know, pressure ratio, what pressure ratio we are talking of, and this is what is a function of what is my temperature ratio. Okay, so let's try to understand what is the meaning and what is the physical interpretation of this equation. Let me put it here. So here if you look at, this is what is representing my compression ratio, and this is what is representing what is my adiabatic efficiency. So here it says my polytropic efficiency, it is say 0.9, and here I am assuming my polytropic efficiency to be 0.92. Okay, so let's try to understand. Suppose if I consider I am looking for my pressure ratio of 4. So for that pressure ratio, if my polytropic efficiency or per stage efficiency is 90%, that's what is giving me my adiabatic efficiency as 88%. Okay, so remember 90% and 88%, that's what is a big difference. Okay, same way here if you look at, if I am taking my polytropic efficiency as a 92%, it says I am able to get my adiabatic efficiency to be say 91%. So just understand what it says, if you are able to design your compressor stage in such a way that you will be having your polytropic efficiency to be large. Okay, that means aerodynamically you are designing your compressor in such a way that the losses are less, then you can say your polytropic efficiency is coming to be high. If that's what is your case, you can say your adiabatic efficiency you are getting to be large. So what it indicates? It says when we are considering, then if we are able to increase, let me go back here, it says if I will be dividing my compression process with more number of compressor stages, then we can say we are able to achieve this temperature rise to be small, and that's what will be giving me very high temperature ratio, and that's what will be giving me higher efficiency. So it says if you are adding the number of stages to your compressor, then you are able to increase your efficiency. Now when I am adding my number of stages to say my axial flow compressor for engine, that's what will be increasing my length of the engine. Suppose if I am targeting, say we are having our aero engine, that's what is in target, where if I will be increasing my number of stages. Why I am increasing my number of stages? Because I am looking for my polytropic efficiency to be higher, because I am looking for my compressor efficiency to be higher. Then what will happen? My number of stages that will be increasing, it will be increasing the length of my engine. Again, that's what will be increasing my drag. And when we are talking about say commercial aircraft where my efficiency is of major concern, okay, and our fuel economy, that's what is major concern. So it says you are restricted with the increase of number of stages. Even when we are talking about say military application, for that military application, what happens? My length of the engine will be increasing. We cannot accommodate that engine within the fuselage, but that's what is being provided for military application. Now you say, sir, this is what is benefit for my land-based power plant. Yes. So for land-based power plant, we are not having any restriction with the length of my engine, gas turbine engine. You can say you can increase more number of stages. That's what people they are doing. Okay, they are putting more number of stages for land-based power plant so that they are able to achieve higher efficiency. They are able to achieve what they are looking for in sense of performance. But you know, like present day, even for land-based power plant, people they are moving towards the concept what they already have used for the aero engine. They are also moving towards the compactness. Okay, so understand one thing. So this is what is a first hint what you need to do in sense of selection of number of stages. Okay, it says typical value of this polytropic efficiency as on today for the modern compressors, that's what is ranging from 88% to 92%. You can understand this number when we say 92%, it's a big number. We are reaching towards our extreme now. Okay, it also says in order to avoid the confusion in sense of understanding, it says my Mach number at the exit of each stage, that's what is remained constant throughout, and that's the reason in place of using static to static efficiency, we are putting that as a total to total efficiency. Okay, and for aircraft engine, conventionally we are writing overall efficiency as say total to total efficiency. Now like we have discussed working of different fluids. Okay, now when I say I'm using different kind of fluids, I will be having my polytropic index, that's what will be different. Okay, now I want to represent different compression process on PV diagram. So let me put those processes between pressure P1 and P2. Now I can do my compression using different thermodynamic process. So you have fundamentally studied in your thermodynamics that if you are looking for the compression, you have different processes. One of the process, that's what we have discussed. It says we can use isentropic process. We have discussed we can use polytropic process or polytropic compression process. We can go with say isothermal process. Okay, and for all this N you can represent, that's what is say for isentropic process, this polytropic index I am putting as say gamma, and by polytropic process it will be within this range, and for isothermal process we are considering my product of pressure and volume, that's what is constant. Now what it says, from our fundamentals, my work required for compression using this isothermal process, that's what is say low, and that's the reason why for many industrial application people they are going with isothermal process. Now the question is, how do we do this combustion or this process or compression process say isothermally? So reciprocating compressor what we are using, that's what is working nearly on this quasi-static way, and that's what we can assume as say isothermal process. Okay, but remember here we are talking about the rotating device which are rotating at very high speed compared to your reciprocating compressor, and that's the reason to achieve this kind of isothermal compression process using this rotating device, that's what is not possible. We are moving towards a polytropic index. Okay, so if my working fluid, that's what is somewhat different, I can represent my polytropic efficiency in this form. It says gamma minus 1 over gamma into n over n minus 1. So we can represent that in sense of my pressure ratio. Okay, and finally my stage polytropic efficiency we are representing as a gamma minus 1 over gamma and into n minus 1. We can say if I am having my process, that's what is a isentropic process for which my n I am putting as a gamma, that's what will be coming in sense. Okay, so this is what is all we are looking for our understanding. Okay, so you know what all we have discussed today, that's what is we are talking our compression process as a thermodynamic process, and we have represented our all stages at the entry and exit of our stage, or entry and exit of our number of stages in overall sense we are representing on TS diagram. Then we have understood what is happening in my rotor and stator, okay, in sense of my TS diagram. Then we have discussed about what we understand for adiabatic efficiency and what we mean by our polytropic efficiency. Later on we have realized your polytropic efficiency, it has gained its own importance, and that's what is giving you idea by increasing your number of stages for the compressor, that's what will be giving you higher overall efficiency, higher adiabatic efficiency. But we are considering adding the stages in your axial flow compressor, that's what is a burden. Okay, and people they are avoiding that kind of situation. Okay, so in next lecture we will be doing with one of the tutorial, that's what will be giving you idea how exactly you need to use this formula for the application. Since this is what is a design course, you need to have some understanding from the fundamental. Straightway we cannot go with the design aspects. Okay, so we will be taking some calculation, some tutorials. I will be giving you assignment also. That's what will be giving you the confidence in sense of use of what all derivations we are discussing here. Thank you very much.